Hello friends, today we are going to discuss indeterminate structural analysis by flexibility method. Basically, all indeterminate classical elastic methods can be categorized under two. One is force method or flexibility method, in which the forces are the primary unknowns, while the second is displacement methods, in which the displacements are our primary unknowns. So let us start today in our session 1, flexibility method. Before going for the method, let's understand first of all what exactly means the flexibility. Consider a prismatic bar AB subjected to axial force P. Due to the action, the bar will deform, and the deformation delta is defined by the elementary equation of mechanics, that is delta equal to PL upon A. If you identify this term L by A, which includes all geometric and elastic constants, so this is the property of a structure in which all geometric and elastic constants are involved. So that property is called as flexibility. So if I derive the unit of the particular that flexibility, then the unit becomes meter per kilonewton or mm per kilonewton. So flexibility is defined as simple meaning. Flexibility is the displacement due to unit force or per unit force. Similarly, if I consider one axial system of bar where external force is P and the reaction will set up at the ends, then this R can also be expressed in force displacement relationship with the means of flexibility like this. Delta is equal to flexibility into R. So hence equation 1 or this equation represents the force displacement relation where displacement is function of force. Now, to get overall idea of a flexibility method and how solutions are obtained for the primary unknowns, consider one simple example. A propped cantilever AB fixed at A and propped at B subjected to external UDL W. Here, as we discussed earlier, in flexibility method, the forces are our primary unknowns. As the forces are unknowns, we are interested to determine what is the static indeterminacy of the given structure. So let's understand first how many are the extra unknowns, that is what is the static indeterminacy of the propped cantilever. This simple equation gives you the static indeterminacy of the structure. ds equal to r minus e, where r are number of reactions. Observe, there are 3 total reactions. Here point to be noted that at fixed end, the horizontal reaction, which will be the axial to the member, is omitted. Only lateral and momentary reactions are considered. So r equal to 3 and equations of equilibrium available, that small e is equal to 2. Only summation Fy and summation moment are available. So 3 minus 2 becomes 1. So that 1 indicates the redundants, that means extra unknowns. So my next point is what? To identify how many extras are unknown, only 1. Let us choose this prop reaction is our redundant. Right? Now, by removing the redundant, in short, by releasing the redundant, the structure remaining is called basic determinate structure. This is important term we are using again and again in our flexibility method. So how to obtain basic determinate structure? Simple 2 steps are involved. First step is to find out how many redundants are there by using formula for ds and identifying the redundant like this, and releasing the redundant gives me basic determinate structure. Now what we will do, considering this basic determinate structure, we will apply all external loads. So whatever BDS we are having, to that BDS all external loads are applied, and again same BDS is considered, but now only redundants are applied. So if the principle of superposition is valid, then this structure with external load plus this BDS with redundant only is original structure. So this is called principle of superposition, which is valid here. Now if I consider the vertical reaction at this prop end is my redundant, then in this direction I am interested to find out what is the displacement when external loads are applied and what is the displacement when redundant is applied. Correct? So now if I observe delta BL, that is displacement at B, that is B point is the point of redundant, due to L, L means external load, and similarly delta at B due to redundant only. So one can write the resultant displacement must be equal to displacement at B due to load plus displacement at B due to redundant. So this particular condition is called compatibility condition of displacement. Now in compatibility condition of displacement, we have known what is the resultant displacement at B in original given structure here. If the support at B is unyielding, then delta B becomes 0. So this is called condition of displacement, and overall equation is called compatibility condition of displacement. In this compatibility condition of displacement, delta BL is certainly known because external loads are given to us, but in displacement due to redundant, here R is the unknown. Redundant R is unknown. So solving this particular equation, we can find out the extra unknowns are there, whatever one, that can be found by compatibility condition of displacement. So this is the overall overview of the flexibility. So as discussed in earlier case, the brief summary of flexibility method is as under. As redundants are only primary unknowns, this is also called as a force method. Then so as to define the number of unknown forces, we need degree of static indeterminacy, the answer of which gives us a number of redundants. BDS, what we have discussed, is obtained by releasing the redundants. And important point is BDS must be stable. So how many forms of BDS we can obtain? One is a cantilever, second is simply supported, third is a simply supported with some overhang portion, and fourth is a determinate hybrid forms. We are going to discuss all these things in further slides, so that understanding the BDS and obtaining the BDS is one of the important job that we will discuss how to do it. And last one is solution to the problem will be obtained by compatibility condition of displacements. Here are some basic equations to find out degree of static indeterminacy for indeterminate beams and frames. In case of beams, general beams and frames, the degree of external static indeterminacy is defined by simple equation R minus E. But if any internal pin is involved, which is called hybrid beams or frames, for that case, the static indeterminacy is given by R minus E minus summation of MH minus 1. This particular parameter or term is to release the internal redundant of the case. The meaning of R, E and MH are as under. But in case of beams, the number of equilibrium conditions are 2, as we discussed in earlier prop cantilever. Only summation Fy and summation M are applicable. But for frames, plane frames, all three equations are applicable. In case of indeterminate trusses, we have to find out external as well as internal indeterminacy. So given by these equations, R minus E external and internal indeterminacy is equal to M minus bracket 2J minus 3, where M indicates number of members, J indicates number of joints. These equations are important as a first step for the solution of flexibility method. Once we get the primary unknowns as a DS, our next important job to identify the redundants and to obtain BDS. Remind what I said in earlier slides, that BDS should be a stable and determinate. And the forms of BDS we can obtain as cantilever, simply supported, simply support with some overhang portion, or one can say determinate hybrid. So this is the important typical skill, how to identify redundants and how to obtain BDS. Let's see by simple examples. Consider one continuous beam ABC, simply supported at A and B, while C is a fixed support. Now my primary job is to find out degree of static indeterminacy. So formula used is ds equal to r minus e. Here observe that number of reactions are 4. Again I will repeat, for continuous beams axial reactions are omitted and equations are taken 2, equilibrium conditions are taken 2. So the formula will be ds equal to r minus e, that is 4 minus 2 equal to 2. That means number of redundants we have to release is equal to 2. So out of these 4 reactions, we have to release 2 redundants. So let's see how many options we can do so that various BDS can be obtained. First option is, let's say I want cantilever to be my BDS. So if I want cantilever to be my BDS, then I must remove this redundant and I must remove this redundant. Only 2 is possible because ds equal to 2. So by removing the redundant or releasing the redundant, we obtain BDS as a cantilever. Once BDS is drawn, show the redundants, that is R1 and R2. Here I want to explain that R1, this number 1 indicates the coordinate axis which represents reaction at A, and in the R2, 2 represents the coordinate axis which represents reaction at B. Which are those to be the redundant? Correct? Now let us see what is the second option. Second option, if I wish to obtain BDS as my simply supported beam. So if I want simply support beam, then I have to select this is my redundant. So, and another redundant is momentary reaction at C. If I remove these two, then balancing remaining structure will be the simply supported AB. So this is our second option where BDS can be simply supported beam. Again after that I am showing whatever the two redundants are selected, this is R1 and R2. Now see third option. In case of third option, let us wish to obtain the BDS with overhang. So if I wish my BDS to be overhang, then these two reactions may be selected as redundant. Releasing that, the remaining structure A, B, C will be the BDS. After showing BDS, show the redundants R1 and R2 as we did in earlier cases. And finally, if I wish to make my redundant such as internal moments, so if I want to select my internal moments as my redundant force, then I have to insert a pin, because we know better in any continuous or rigid structure, if we insert a pin, the internal moment at that point will be released. So sometimes we have to do that so that we can find out internal moments. So let us select B is that point at which the internal moment has to be released. So what one can do, that internal pin, introduce an internal pin at B so that the internal moment at B is reduced, and we will identify this is one of our redundant. So two redundants are selected. One is internal, which is internal moment at B, and second is external, which is external momentary reaction at C. Right? Now after removing the redundant, the structure is shown like this. R1 is the internal redundant and R2 is the external redundant. Important point to note that for internal redundants, we have to show the redundant in pairs, because internal values are always in pairs, equivalent, opposite to each other. So this is the part what we have to learn, how to find out DS and how to find out redundants. Let's take another exercise to obtain degree of static indeterminacy and to obtain the BDS. Consider a frame ABCD fixed at A and hinged at C. Formula to find ds is R minus C. So number of reactions here are 5, 3 at A, and at hinge support C there are 2 reactions, and we are going to use all 3 equations for plane frames. So 5 minus 3, the answer becomes 2. That means we have to identify 2 unknowns as redundants. So consider I wish to obtain a BDS as a cantilever. So to maintain the cantilever, let keep support A as it is, and whatever 2 reactions here, those are identified as redundant and those are released. So after plotting BDS, we have to show the identified redundants R1 and R2. In second option, we have to select overhang. So in case of overhang, I wish to remove the momentary reaction at A here and horizontal reaction at C. So these 2 reactions are considered as redundants and those 2 are removed. So remaining structure is BDS. and after that BDS is plotted, show that two redundant reactions. After learning how to find degree of static indeterminacy and how to obtain BDS by releasing the redundant, our next job is to understand how to find out displacements. In elementary subjects of structural analysis, we have learned many methods to find out displacements. Some are based on geometric ideas and some are based on mathematical tools. For example, Macaulay's method, moment area method, conjugate beam method, Castiglione's method, so many methods we have learned. But most frequently used and with ease is unit load method for displacement, which is based on principle of virtual work. Now this is best suitable because for any complex geometry, the method is best suitable, which is given by two simple equations. One is displacement due to external load, one formula is, and second formula is displacement due to unit load. Let me clear, when I say displacement due to unit load, it is nothing but a flexibility, because flexibility we have defined as displacement at any point due to unit load. So using principle of virtual work, method of unit load displacement, we can find out displacements due to external loads as well as flexibility coefficients. Let's understand these two equations which are derived from the Castiglione's theorem and principle of virtual work. Here, displacement due to external loads is termed as delta IL, where I is the point at which displacement we are determining, and L indicates the due to load. So delta IL means displacement at point I due to all external loads, which is given by sum of integral m dot mi upon ei with respect to dx. Here m indicates bending moment equations when all external loads are applied, and small m indicates bending moment equations again, but unit load is applied at point I. So this point is very important to know, m dot mi. Similarly, to find out any flexibility coefficients, that means delta ij, or one can call fij like this, fij, flexibility at I due to j unit load. Here delta ij means displacement at I due to unit load at j. Right? So formula is again same, sum of integrals mi dot mj upon ei with respect to dx. Again here mi means bending moment equations in the beam when unit load is applied at I, and mj means bending moment equations in beam when unit load is applied at j. So these two fundamental equations are useful to find out the flexibility coefficients as well as displacements due to unit load. Right? So where m are the equations for bending moment due to BDS, as I already explained, and m is okay. Now let's practice the unit load method for displacement. Here we are targeting only displacement at C in vertical direction. This is our object, to find out vertical displacement at C, delta CL. For that, the first figure we have to plot as a M diagram with all external loads, and second figure small m diagram with unit loads. In second step, we are going for bending moment equations in different segments, and in third step we are going to find out displacements at desired points. So let us follow steps one by one. Okay, M diagram means what? BDS with all external loads. So BDS is already cantilever structure is the BDS, and I have shown all external loads here. Then to find out reactions, so using equilibrium condition, summation moment equal to 0 and summation Fy equal to 0, let us find these two reactions at the fixed end. After that, small m diagram, as I said earlier, small m indicates application of unit load at desired location. Our desired location is vertical displacement at C here. So I must apply unit load in vertical direction at C. The direction assumed is downward. You can assume upward, no problem at all. Later on we will discuss on this direction upward and downward. Again find out reactions at A due to that unit load, and after that, so as to facilitate BM equations, we have to take sections. So we have two segments, segment AB and segment BC. So in segment AB, let us take one section at distance x from A. Now for the segment AB and with this distance x, we have limits of this section from 0 to 4. Because AB is our region, so this section has limits 0 to 4. Similarly, take second section in BC with respect to C as origin. So again, total BC length is 3 meter. So limit for the x here within the range BC is x starts from 0. That means lower limit is 0 and upper limit is 3. Once that is over, I am ready for BM equation table. Understand this one by one. Now here I have to write all the BM equations due to the external loads, and here I have to write all the BM equation due to unit load. Correct? Okay, let's start. Now consider segment AB. In this segment AB, A is selected as origin, and as I discussed, limits are 0 to 4, and for AB, the value of geometric constant I is I, inertia, moment of inertia. Now we have to take moment of all the forces about this point and considering left FBD because we have taken x from left side. So force into distance 220 is the force and x is the distance. If I try to rotate this force about this point, it will cause rotation like this. So this is the sagging shape. So 220 into x is taken positive, it is here. Then 890 is the moment. So moment is taken as it is, but it is going down like this. It creates a hogging. So minus 890 is written here. And there is one UDL. So for UDL, it is acting downward. So total UDL on left hand side of the section is 25 into x is the UDL. And distance from the point, this distance is x by 2. And it is creating hogging moment. So equation becomes 25 into x is the UDL. Into x by 2 is the distance. So 25 times x square by 2 and it creates a hogging. So it should be minus 25 x square by 2. So this is regarding M. Now considering small m diagram, we have, this is the section. We have to take moment at this particular point. Then force into distance creates sagging. So 1 into x positive. So only x is written here. Then this is the moment, but it is going in hogging shape like this. So minus 7 written here. So like this, for segment AB, considering M diagram and considering small m diagram, we have prepared row number 1. Similarly, for segment BC, same process we can follow. For segment BC, we have taken origin as a C because x is assumed from the C. Limits for BC is 0 to 3 and inertia value is I. Correct? Now, in segment BC, we have to take moment at this particular point here. Then force into distance creates a hogging moment. So minus 70 into x, it is written under M diagram. And in case of this one, small m diagram, we wish to take moment at the section point here. So force into distance, again this will create a hogging. So minus x, 1 into x is x, so hogging is minus, so minus x. So this is the way how we obtain BM equation tables. When that step is over, now we are ready to use the formulas what we have explained in unit load method. What is our target? To find out vertical displacement at C due to external loads. Formula is m dot mc into dx, where m are these values and mc are these values. So putting the values in the equation, delta CL equal to two integrals will come because we have two segments, segment AB and segment BC. So whatever segment AB is this is our segment AB and this is our segment BC. In segment AB, the first bracket, this bracket is your M bracket and second bracket is your small m bracket. Correct? Like that, for second bracket, second segment BC, the first bracket is M bracket and second bracket is X bracket. So putting the values and solving for integral, we get the answer delta CL is equal to 11870 upon EI meters. Unit here meter because it is a displacement. If it is a rotation, then I am having unit of radians. First point to discuss. Now second point to discuss is I have shown displacement is downward. Just recall, in last slide I have said that unit load assumed is downward. If the displacement answer is positive, then the direction of displacement takes place in the direction of unit load assumed. Suppose my answer is negative, then definitely I would say displacement is vertical, because we have assumed downward unit load in last slide. So when whatever answer positive indicates the assumption is correct, the displacement takes place in the direction of unit load. So this is the way how displacements can be plotted. Okay, now let's move ahead. These are my two redundants, identify redundants R1 and R2. The compatibility condition what we have discussed earlier is delta I is equal to delta IL plus delta IR. Here delta IL can be found directly because loads are given and known, while in delta IR, that is displacement due to redundant, R1 and R2 are our unknowns. So that is converted into flexibility into R. Expanding this form, for two redundants I can write delta 1, that means displacement at coordinate axis 1 at R1 and displacement at coordinate axis 2 R2, that is delta 2. So delta 1 equal to delta 1L displacement at 1 due to loads plus F11, that is flexibility at element 11 and R1 plus F12 R2. Similarly for delta 2, delta 2L plus F21 R1 plus F22 R2. Understand the meaning of F11, F12 like that. F11 indicates what? Displacement at 1 due to unit load at 1. Similarly, F12 means displacement at 1 due to unit load at 2. So this is the idea how the flexibility coefficients are. This is the expansion for 2 by 2 matrix. If I have 3 redundants, then I can expand the equation 2a like this: F13 into R3. Like that, I can expand the equation for n by n matrix, that is F1n into Rn, like that. Now, if I write the equation 2a, 2b in matrix form for 3 by 3 matrix or n by n matrix, it is like this. So this particular matrix is called flexibility matrix, which has square matrix n by n size, where n indicates the number of redundants, and number of redundants we know it is given by degree of static indeterminacy. Important to note that all the elements on principal diagonal are always positive because those are F11, F22, Fnn. And we know that Maxwell's reciprocal theorem is applicable here. So one can say that Fij is equal to Fji. Means what? F12 is always equal to F21. So one can say the flexibility matrix is always square, symmetric, and all elements on principal diagonal are always positive. So these are the properties of flexibility matrix. As per Maxwell's reciprocal theorem, Fij equal to Fji. Second property is it is always symmetric matrix. So we have to define either upper triangle or lower triangle. We need not to find out all elements. Third property is it is always square matrix of order n, where value of n is nothing but your number of unknowns, which is given by degree of static indeterminacy, and elements on principal diagonal are always positive. So here we are completing our session 1, which has some review points I want to consider. First is flexibility or force method is a classical elastic method of structural analysis, and as we are adopting matrix, it is called matrix approach. Second point is redundant forces are our primary unknowns. So to get the redundant forces, we want to find out degree of static indeterminacy. But important point I want to quote here is whenever yielding of any support is mentioned in the problem, then the corresponding reaction must be chosen as one of our redundant. This is very important because any yielding of support will cause action reactions at other places also. So we have to select that corresponding reaction as one of our redundant. We will see this in our session 2 when we will solve certain problems. Third point is Displacement due to external loads at coordinates of redundants and flexibility coefficients are derived by unit load method. One example also seen how to employ unit load method. Fourth point to discuss is flexibility matrix is always square, symmetric, having positive elements on its principal diagonal. And fifth point is to obtain the solution for unknowns, we have to employ compatibility condition of displacements. So these are some review points of our session number 1. So friends, we arrived at the end of session number 1, in which we have learned the fundamental principles and the formulas which are applicable in flexibility method. For solved problems, I request you to visit the second session on flexibility method. Thank you very much.